Okay, let's just get started. Make sure this is working. All right, great. Thanks so much for everyone coming for this tutorial. As you can see from our name, it's going to be learning and decision making from ranked data. So hopefully I will tell you a few recent development in this field. Actually, it's a pretty old field, interdisciplinary field. They've been studying computer science, of course, and statistics, economics, and more recently, computational social choice. But I think we have something new to say. All right, so just think about the following problem. I'm sure that many of you have encountered a similar problem in some stage of your life. Suppose your department is hiring a new faculty member to have a new opening, right? So after the phone interviews, you're going to invite 3 guys for on-site. Let's call them Eric, Kyle, and Stan. Oh, okay. I'm sorry about that. Oh, I'm a little bit worried this is too loud, but because usually I'm in the class, I yell in front of 200 students. So, but anyway, so we have invited 3 candidates for job interviews. Let's call them Eric, Kyle, and Stan. After the interview, the committee member is going to vote to decide who will be the winner. Of course, who will be the winner to give the offer. But of course, you have multiple rounds of discussion and decision. But let's say each of them gives a full ranking over the candidates to represent his or her preferences. Here, ranking just means a full ranking. You must specify who is your top choice, who is your second choice, who is your third choice. Formally, it's called a linear order. But for example, the first guy says, I would prefer this green guy, Kale, to the blue guy, Stan, and to this, well, I don't know, weird guy, let's call it Eric. And then they're going to use a voting rule to choose the winner. Let's say they use the most commonly used voting rule in the world. Well, in Australia, it is STV, but in other part of the world, it's a plurality. It's a very simple rule, right? So just look at who is your top choice. Just ignore all of the rest of the preferences. Look at the top choice, head count. How many times people voted for Eric? How many times people voted for Kyle? How many times people voted for Stan? And you basically just choose the one with the highest number of head counts. And you see that there is a tie, right? So Kyle, Stan, Eric. And in terms of whenever there's a tie, let's use the alphabetic tiebreak. And this time, Eric will be the winner. Okay, so far so good. Seems like the problem is solved. But let's take a closer look at the first guy's preferences. Eric is his last choice. He actually can do something better by submitting a false report. Suppose his true preferences is Kyle, Stan, Eric. But what if he lies? What if he says that my true preferences is actually Stan, Kyle, and Eric? In that case, we're still using the same rule, same tie-breaking mechanism. You can see that Stan would be the winner because Stan would have got 2 votes versus 1. Now, what's the point of this? The point is that by lying to say that Stan is my top choice, this guy, the first blue guy, can actually improve the winner from Eric to Stan. So that means, condition on him knowing preferences of the other guys, he has incentive to lie about his preferences, at least in the plurality voting setting. So if you attended tutorial yesterday in the afternoon, there's a whole tutorial around strategic voting and strategic candidacy, but I'm not going to repeat, of course, not going to repeat that. But this just shows a very interesting problem. Say we have a group decision-making problem from ranked data. Everyone gives a ranking. And what are the criteria? So of course, so we want to choose a best candidate for our department. So how can we evaluate the quality of this candidate? You can say, well, it looks like he has many publications, but hopefully he will continue publishing this nice number of papers in the future. He probably will bring us some grant, probably will be a good teacher, probably will be good colleagues, but all of these are unknown. So you can only have some idea of how it works, the quality of this candidate from what you have observed. So this is more like evaluating from the statistical point of view, what is the quality of the candidate conditioned on the information you had so far. And another interesting is that we need fairness in this procedure. So just like in standard machine learning, sometimes you don't really care about fairness. You just want to find the mechanism or classifier with the smallest error rate. But a few months ago, when our department is hiring, some faculty members actually voluntarily says that, I know nothing about this field, for example, HPC. Can I voluntarily abstain from voting? And the answer from department chair was immediately no, because we are a good department, we are a democratic department, so everyone must have 1 vote. We must have a fail mechanism, even though you think your vote is extremely noisy. So there are some situations in real life you really need fairness, which I've just encountered. And we want to take care of strategy proofness, right? It'd be great if there is a mechanism, well, no one has incentive to lie, so that you are kind of aggregating the nice part of the preferences, but not the false preferences. So there's actually more complicated story behind it. If I've heard of this implementation theory in economics, the story is not always like we want truthful preferences, but let's just say it'd be great if there's a strategy proof mechanism. And finally, we want this mechanism to be computed hopefully in a reasonable amount of time. So certainly you don't want to say, we have a great mechanism, but the winner will be announced in 10 years, but well, this guy's already accepted other offers. Okay, so this might be look like just an toy example, but I think there are many other situations where we have encountered the problem of learning and decision-making from ranked data with respect to these three types of criteria: statistics, economics, and computation. So for example, in the voting setting, and also in the jury setting, which I'm going to tell you one of the most famous theorems in probably mathematical political science called the Cottagers Theorem. I'm not sure if people know a little bit about the jury system, right? So it's actually a very funny system. So who decide and suspect is liable or not? Usually would say it's judge, but at least in the United States, some random people from the street will be called on for jury duty. I was actually received an email, and the email says that if you don't come, even though you are not an U.S. citizen, if you don't come, it's a violation of U.S. law or whatever. So you have to have some random people on the street, and they come to the court, listen to the evidence of both guys, and vote to decide if this guy is liable or not. Very interesting system. So why this is a good system in the first place, right? So what if you just like you called me and I know nothing about animal ethics or whatever, and then I'm going to decide this guy's future. That sounds strange, but we see some mathematical foundations behind this. So similar problems in marketing, so very influential papers probably behind McFadden's Nobel Prize. So based on this user's behavior, you want to predict the demand curve of a new product. For example, when San Francisco area BART was built, before it was built, McFadden was running this regression using the model that is closely related to one of the models we'll talk about, and it was a very accurate prediction. Also in marketing, right? So, and of course also in what is it called? Meta search engines, or sometimes it's called learning to rank or information retrieval, whatever you want to call it. You have multiple rankings from multiple search engines, and we want to aggregate them to hopefully produce a good ranking, revealing the true ranking over the websites. And also in Amazon Mechanic Turk and other crowdsourcing websites, where you have these noisy answers from the users who may or may not have incentive to lie, or just not put in efforts and give you some random numbers to collect the 20 cents. Here we want to incentivize them to give true preferences, and we want the mechanism to be strategy proof, hopefully as much as possible. In recommendation systems, well, you have some partial data about this user's behavior. You want to recommend good movies by predicting what they're gonna like, and so on. So in healthcare, defense, business decision making, recently there's a very big collaboration between IBM and RPI building this immersive environment room. So just like somebody's talking in this room, and then the room automatically recognizes the contacts and then help them to make a decision. For example, deciding which company to buy among a list of thousands of companies. Okay, so there are many examples. I can give you references to the applications of these examples, but it's just too much to put on this slide. Now, why do we care about ranked data but not cardinal data? Of course, you would say, everyone gives me a number. So let's say your preferences or the strength of preferences about these candidates, why not? Well, the reason is pretty easy, because it's much easier for people to rank a set of candidates instead of giving each of this candidate a number. So that often leads to big data set, and that's one of the motivations we really care about computational aspects. Okay, so let's just a little bit of motivation of this tutorial. Let me talk about one of probably the most important theorem in mathematical politics, which is the Cottagers Theorem. It's a very simple theorem. As you can see, that was discovered 232 years ago. And at that time, there's almost no statistical science yet. So even though it looks pretty naive in the statistical science, but just please consider the context. So what did it say? It says that, let's say we have two candidates, call them Obama and McCain. By the way, McCain just had a pretty bad disease recently. But anyway, so we have two candidates, Obama and McCain. One of them is a good candidate for the president of the United States. But every voter is going to just vote for one of them. What is the probability of voting for one of them? Well, it depends on the quality, depends on whether or not this candidate is the best candidate for this position. Let's say every voter is flipping a coin, a biased coin, to decide whom to vote for. And the probability of voting for one candidate or another depends on the ground truth, which is not directly observable. So if you're familiar with the statistic, that just tells you that there's a statistical model where in the ground truth, in the parameter space, we have two alternatives. We have Obama and McCain. And the sample space, every voter gives a vote. You can say it's Obama preferred McCain or McCain preferred Obama, but let's just say each voter independently vote for McCain or Obama with respect to the following probability. Well, there exists a number, P, fix this P, strictly between 0.5 and 1. If the ground truth winner, if the best candidate is Obama, then the probability of independent voter voting for Obama is the same as if the ground truth is McCain and he's voting for McCain, which is exactly this magic number P, strictly at 0.5. Okay, so under this statistical model, what does the jury theorem say? This is just the specification of the model, IID sampling, and what this conditional probability is actually not conditional probability, but let's just pretend it's conditional probability, pretend that we are Bayesians for the most part of this talk. And then the theorem basically just says that as the number of votes goes to infinity, let's just use majority voting or plurality, because I mean, when you have two candidates, plurality is the same as the majority. We just use the majority voting. The winner of agent's profile converges in probability to the ground truth. So basically, how to interpret it just says that we have a large number of samples. The majority of the samples reveals the ground truth with high probability, and probability goes to 1 as n goes to infinity. So if you have taken statistical course, this is called consistency of the estimator. So it's pretty important theorem, as somebody noted that it lays, among other things, foundations of the analogy of democratic regime. So I'm sure I can find many other good words about it on Wiki. So any question about this quick theorem? The proof was done by Laplace, the famous Laplace. If I learned Laplace transformation, whatever, that's him. So, so this guy actually interesting. So when this guy actually discovered this theorem, he stated in a very vague way and didn't give a proof, because it's actually not true proof. So you can think about it. If you're not using it using the central limit theorem, you pretty much have to prove the central limit theorem by yourself. To some extent. But anyway, so it's a very important theorem in history. But does it mean that actually there's nothing we can do? Because just think about it. We want a good estimation. We want a good mechanism that satisfies good statistical property, economic property, as well as computational property. But now we have a mechanism which is majority rule, which is actually pretty good. Actually, it's the best among all possible mechanisms in this situation. For example, it has great statistical guarantee, converges to ground truth when we have large samples. It's perfectly fair in the sense that I'm going to talk very briefly in the second half of the talk. I mean, we in social choice have some mathematical definition, rigorous mathematical definition of fairness, and majority just satisfies all of them. And it's strategy proof. Just think about it. There's no incentive to lie. If you truly think that Obama is the winner, voting for McCain will just decrease the chance that Obama is going to win. Okay? So perfectly fair. And it's very easy to compute, right? Just head count, right? Majority, how hard it is to compute. So problem is solved. Well, as you can see, that what if we have, the problem is that, what if we have at least 3 alternatives? Things just breaks down, and then that's pretty much leads to the field of social choice theory, among many other things. Okay, so pretty much this talk will be about, you can assume the number of candidates is at least 3, because that's the problem where the learning and decision making becomes really interesting. So the overview of this talk would be also the framework. Say we have a bunch of agents. Each of them has preferences over some candidates or alternatives. And we have systems, a computer-aided system, to help them to make a decision. Now, how this decision is going to be made? Of course, these guys should first submit their preferences to this computer system. It would be great that actually the computer system can read their mind and automatically figure out their preferences, which sounds like sci-fi. 5 years ago, I think I gave similar talks, not on this topic, a couple of years ago. But at that time, there was no such fancy stuff. But there are such fancy stuff recently. At least I've heard that Brent Venerable or whomever others group at Tulane University, they have really this device that you wear it on your head, and then it's kind of reading your preferences, reading your brain wave, whatever. So maybe that would change the field, but actually still, let's for now say that everyone submit their preferences to the center. And the center is going to learn about this, learn and reason about these preferences. Let me keep it vague for now. And for most of the part of the talk, we'll be using probabilistic learning and the statistics. So let's say the center has some probabilistic knowledge about this guy's preferences. Of course, he's not 100% sure. So sometimes the center may ask the agents to provide more details about their preferences. Say, your preference is not very certain, so what do you think about A versus B, and so on. And then after multiple rounds of this is called elicitation, the center hopefully would have a better idea of this guy's preferences, and finally the center is going to give a decision, hopefully help these guys to make a correct and fair and quick decision. Okay. So this three part corresponds to the three topics of this talk. The first part of learning, we're going to spend most of time on it for whatever reasons, just because it's so interesting to learn many statistical model and algorithms. And the second part, we're going to talk about elicitation. Initially I thought I should have more slides on it, but it turns out that I would be running out of time. So 3 slides exactly. If not 3 slides, you can blame on me. I will give you a ginger chew for that. So 3 slides on elicitation and an hour on decision-making principles and algorithms. Okay, so before that, before we start the learning part, let me be more specific about what is the rank data. So in this talk, we are mostly focused on linear orders for rankings, but we also talk about some other types of preferences. Say linear order, we have 3 candidates or 3 alternatives, Obama, McCain, and Nader. And linear order just says that mathematical definition, you can ignore it, but it just said that you must specify who's the top rank, who's the second rank, who's the third rank, and the preferences are strict. And in terms of the graph, this can be visualized in a graph. Well, the vertices are the candidates O, M, and N, and there's edge between some candidates. For example, O to M means that O is strictly preferred to M. So these preferences must be strict and transitive. So here. The second part, we probably will touch, you probably have some idea about it, is called weak order. In other words, it's actually just ranking with ties. So here, O and M are tied for the first place, N is tied for the second place. And the third part third type of preferences is more general partial order. Any order satisfying transitivity is a partial order. For example, this one, O prefer to M, prefer to N. So basically, actually, you have O prefer to N by transitivity. But a specific type of partial order is pairwise comparisons. Say, even though we have multiple candidates, but let me just ask you, which one do you prefer, O or M? So that's pairwise comparisons. So any quick question about what does mean by rank data? We basically just mean binary relations, but satisfying some axiomatic properties, especially transitivity, and for most of the part, we'll be focusing on linear orders, but we'll also touch upon other type of preferences. Yes? Yeah, so that's actually a bad example. So let's forget about this one. So probably we just forget about the pairwise comparisons. So yeah, so certainly you have this transitivity, if I am correct. So, but anyway, pairwise comparisons are probably more relevant over here. Okay, so just to emphasize, most of the talk will be focusing on linear orders. That means everyone submitting a full ranking over the set of candidates. So to just give you some idea of this type of preferences, and let's do a quick experiment, which is also related to the rest of part of the talk. May I ask everyone a favor? If you have a smartphone and if you have a QR code reader, can you go to this website and try to submit something? So I'll think more about this website. Offer.io is actually developed at our university. It was holding our a polling for our student government election, which happened for it's already happened for 150 years, and it's going to be half official for the upcoming elections. So, but we see all kinds of user interfaces for you guys to submit preferences. And if you don't have smartphone, please use this link if possible. I think that is not issue for us. So I'll show you how this works, just as a quick example. And actually, it's a funny topic to vote on. So how many of you actually realized that last year, 2016, there is a panel held at Stanford University about, I think it's called 100-year study of artificial intelligence. So if you haven't read that paper yet, please, I highly recommend reading it. It identifies, I think 10 or 11, don't remember exactly, fields for kind of future research. A very nice overview, but also a few kind of hot areas and practical areas for future research. And the topics I was asking you to vote on are like, which one do you think will be more promising? You can give a linear order. You don't have to, because ranking 11 of them might be pretty hard, and some of them I have no idea about, like neuromorphic computing. So what is that? If you don't Google it, if you don't work on the field, I don't know what it means. So sorry to say that, but okay, let's say algorithm theory and computation social choice. If you don't work on it, you don't know what it means. I'm happy to say it's very comfortable saying it because that's my own field. So, but anyway, so you don't have to use a single user interface. So this is what it's supposed to be. And voting is anonymous. So feel free to vote anything. You can also put random comments if you want. That would be appreciated. So we have a couple of user interfaces. We have 2 columns, 1 column, slider, star, yes, no, corresponding to different type of preferences. So for the 2 column, you can see that maybe on the mobile it's slightly different, but on the so here on the left-hand side is the preferences you want to submit. On the right-hand side are the remaining candidates. What you can do is that you can click the one on the right, and then it will be immediately moved to the left. For example, I click algorithm, game theory, and computational social choice. It was moved to the first place. And then I'm clicking, let's say, deep learning, reinforcement learning, computer vision, crowdsourcing. You can merge them and create ties because that's going to be weak orders. You can switch it around, and you can submit a partial order. So for example, I don't need to submit my preferences for the rest of things because I have no idea about them. So you can basically just submit it, and it becomes pretty slow for whatever reason. And then you can watch the result, live result at some point. So we will back to the live result because it's related to machine learning later on. But this is a 2 column. 1 column is same, except that you're starting with everything and you need to merge it and submit your preferences. Slider is basically just giving scores. If you can give scores, that may help things. But if you cannot, just use the ranking would be pretty nice. Stars is same as slider, but just at a scale of 10 instead of 100. And yes, no is what people call approval voting. So there are a couple of them that say your preferences are dichotomous. A subset of alternatives you think are nice, you approve all of them, but you don't say which one you like better. But you think those approved candidates are more preferred to those unapproved candidates. So basically you just click, you can click multiple of them. So let me just deep learning, computer vision, crowdsourcing, and NLP. And then you can submit your preferences. You can submit preferences at your wish, and you can come back and change it at any time. So this is something to work at if you can. So please, we can see that if our votes actually aggregate we can find the ground truth, let's say, around this audience. But we'll see. So, but it's hard to verify the ground truth, right? So unless you probably after another 100 years, we can come back and see if this particular audience actually help us to reveal the ground truth. Anyway, to give you some idea about preferences. Are there any questions? Okay, so let's start with the exciting learning part. Now, here's a very quick overview of the learning part. So we must deal with rank data. So we're first going to talk about some popular statistical models for rank data. We're going to talk about two types of models. The first type is called distance-based models. So essentially, the probability of generating sample depends on the distance, how far away the sample is from the ground truth in a metric space. So this is mostly the model studied in statistics. So one is called the Malus model, it's a statistician, and the other one is Condorcet's model, which is natural generalization of Cottagers Theorem's model. Okay, so the second type is called random utility models. I would be more specific, but if you have heard of Planck-Lewis models, it's a natural generalization of logistic regression to multiple candidate space. So this is a model mostly pursued in, for example, psychology, cognitive science, and economics. And finally, we'll be talking about mixture models, so which is a flexible way of creating new models based on existing models. So for example, you can combine two Malus models, creating a mixture model. You can combine a Malus model, a Planck-Lewis model to create another Planck-Lewis model. So this is a very flexible way of creating many models. So this is about the models. We'll also be talking about inference algorithms, especially state-of-the-art inference algorithms, and those are mostly at the intersection of computer science and statistics. We've been focusing on two of the most famous type of reasoning techniques, which is the maximum likelihood estimator, MLE, and the Bayesian, not really Bayesian estimator, but more like Bayesian approach, which I'll be more specific later on. So I'll be talking about the state-of-the-art algorithms about maximum MLE and Bayesian for these models. Okay. So what is a statistical model? So if you've learned statistics, please just feel free to skip it. But just in case that some of you haven't, which is certainly not a big shame, because before I worked on this type of topic 5 or 6 years ago, I know nothing about statistics. And after learning it, I feel that many problems are actually just solved if you are clear about the mathematical definition of statistical model. It's a little bit boring, but I will give you examples, and that might be something interesting to learn or reinforce yourself. Okay. So usually a statistical model has three parts. The first is called a parameter space. Let's call it theta. The parameter space models the true state of the world. For example, you can say theta composed of all of the orientations of atoms in the world. But usually in the modeling, you're just keeping the relevant type of information. So that's a ground truth we want to reason about, but usually you don't directly observe it. And second part is called a sample space. This is the part you actually can observe. Let's say a sample space in our rank aggregation problem is that it is composed of n rankings, each from n voter. Okay, so throughout this tutorial, I'm going to use n to denote the number of voters, number of data points, if you want. So rankings, it's a little bit vague, but for most of the part, it's linear order. But whenever it is not linear order, I will be specific. Okay, and A is a set of alternatives and number of voters here, and we're going to assume that votes are IID. Strictly speaking, you don't have to in the most general case, but for this talk, we're going to always assume that votes are generated IID. And the third part, and arguably the most important part, is a set of probability distributions over the samples. So the way statisticians model this world is that suppose the ground truth is theta, okay, which you don't observe, then we're going to have a distribution over the sample space. So basically, mathematically just means that for every theta in the parameter space, we're going to have distribution over the sample space. But here it's compactly represented because we're just going to have to specify distribution over all rankings. But then, because of votes are IID, so the probability is just very naturally generated to that case. Okay. So there are two quick notes. The first is that sometimes parameter space are omitted. It's not really necessary. It doesn't really matter if you call this a cup or it's base in Chinese. So it's the same thing. So it doesn't really matter if parameter space is necessary. What really matters is what it looks like, how hard it feels, and how can I use it. So in other words, what's really useful is the distribution. So whatever you call it, it doesn't really matter. So parameter space is just a space to index the set of distributions. That's actually a pretty important note that I kind of learned. It's probably a statistician, statistic teacher taught you, but sometimes you feel it's actually pretty confusing and important part. So sometimes another important part is that, so this is not a conditional distribution. So the set of distribution is indexed by theta for each of theta in the parameter space, but this is in no way a conditional distribution. If you are Bayesian, you can say it's a conditional distribution, but eventually it's actually just a distribution. But sometimes, that said, I'm going to confuse you because for most of part of this talk, I'm pretending that I'm Bayesian. I'm going to write it down as, given the ground truth theta, the probability you see a particular ranking. Okay. Are there any quick questions? Okay, examples. Maybe let's hold on to our question about examples. In a compensatory setting, we have two types of ground truths, right? So Obama is the correct winner, and McCain is the correct winner. So the parameter space has two candidates, and the sample space has ID votes. Each of them either vote for Obama or vote for McCain. And probability distribution just says that given ground truth is Obama, so the correct way to specify is to move this Obama to a subscript, but I said that let's pretend us to be Bayesian. So given the ground truth is Obama, the independent vote is voting for Obama is the same as given ground truth to McCain, independent vote for McCain, which is P strictly larger than half. So we didn't specify what is the probability of McCain given Obama because that's just 1 plus P. That's a probability distribution. Okay, cheap example, but slightly more sophisticated example is Mel's model. As I promised, it's one of the distance-based models, but the formal definition is that we have a dispersion parameter. It's positive, sorry, it's strictly between 0 and 1. And the parameter space is composed of all 4 rankings over the candidates. For example, here is a 4 ranking, right? It's acyclic. Eric, Stan, Kyle. And the sample space is composed of ID generated 4 rankings as well. Now the probability is that given the ground truth rankings W, the probability of generating an ID generated and ranking V is proportional to phi, this dispersion parameter, raised to the Cantor distance between V and W. So you see that the Cantor distance larger means that this probability is smaller. So what is Cantor distance? It's very easy. So just look at all of the pairs. Okay, we have 3 pairs over here: Eric, Stan, Kyle, Stan, Kyle. So look at only 3 pairs. How many pairwise comparisons are different in V and W? So that's the Cantor distance. So of course, the Cantor distance 0, that's exactly the same ranking, and the Cantor distance is, largest Cantor distance is M choose 2. Here, M is number of candidates, right? So for every pair, it's different. So basically just inverse order, and that's how it works. So just to give you a more concrete example, because I really want to make sure the model is correct, because otherwise the algorithm doesn't make sense at all. So let's say the ground truth is Eric, Kyle, Stan. Let's look at this one, right? So if the ground truth is Eric, Kyle, Stan, the probability of generating this ground truth is phi raised to the Cantor distance between this ranking and itself is 0. So it's proportional to 1, but you need to divide it by a normalization factor constant. And let's look at this one. This one is completely inverse order. So what is the Cantor distance between Eric, Kyle, Stan and Stan, Kyle, Eric? Well, all of the 3 pairwise comparisons are different. So the Cantor distance will be 3, and that means the probability of generating Stan, Kyle, Eric is phi raised to cubic over Z. Z is the normalization constant. So if you want to verify, you can verify that all of the 6 rankings sum up to 1. Okay. Are there any questions about Mel's model or statistical models in general? Okay, let's move on. Another model, Cottagers model, is slightly different. It's still based on on the Cantor distance, but as I said, that not always the parameter space are linear order. So what if the parameter space contains all binary relationships? For example, possibly cyclic rankings, which we actually didn't talk about, but let's just give it a very quick look, because this will not be the main topic of this talk. but it's an important model which I think that is worth talking about. So the parameter space and the sample space are all composed of possibly cyclic rankings. And in that case, you can still define the counterpart distance, right? So just look at all of the pairwise comparisons and see how many pairwise comparisons don't agree with. And the probability is almost exactly the same. So look at formula is exactly the same. It's proportional to phi raised to the counterpart distance between these two rankings, the round trip ranking and the generated ranking. Here, ranking means binary relations. So yeah, so just another example of just color. So this gives you a whole set of models called distance-based models. Say we have, let's say, the parameter space and the sample space are all composed of 4 rankings. Now, given a metric space, T, for example, T can be a set of 4 rankings, and another metric, a distance metric over it, D, measures how far away that each of them is. Each pair of this is, and a fixed dispersion parameter. Everything else is pretty much the same. The parameter space is T. The sample space is T raised to the n because we have 1 vote from each voter choosing from T independently and identically. And probability is just given the ground truth W, and you generate V proportional to phi raised to the distance. So the closer the V is to W, the higher probability you're going to generate it. So while we're defining it, there are many other distance metrics you can look at. For example, K-like distance, which I just don't need to define because it's relevant. But most interesting, probably the most famous model, distance-based model, is Mallows, and we're going to focus on Mallows for most of part of the talk, and I'll probably talk about some results about Condorcet's model at some point later on. All right, so that's question of, that's the end of the first model, mostly by statisticians, the distance-based model. Now let's talk about a completely different set of models. It might be slightly confusing because now it might be a little bit hard for me to give examples, but please, if you have any questions, feel free to stop and ask me. So I'll be very happy if you can follow it. Everyone will be on the same page. So that's the main purpose of giving this tutorial, right? So it'd be interesting to really just help people to learn something, but not just provide a list of recent results. So that'd be a kind of, tiring to learn. But anyway, so maybe that said, I'm still doing this kind of things, but feel free to correct me if you want to stop me and ask questions. Okay, so this is called random utility models, first proposed by Thurstone. This guy actually did not one of our prize. So it's different from the previous one. So it's a continuous parameter space. So more like a standard optimization problem. Let's say we're just going to use some notations. Let's say we have m candidates, m alternatives. Each alternative is modeled by a utility distribution. It's not just modeled by a number, even though you can, to some extent later on, parameterization of this distribution, but eventually it's modeled by a utility distribution. And so theta I is basically just a vector, usually it's a vector that parameterizes this utility distribution. For example, for Gaussian distribution, you can parameterize by mean and variance, or you can say it's just parameterized by the mean if you fix the variance. So different ways of modeling it, that means that this is a very general model. Now, this is a parameter space. So how can we generate a data point? How can we generate a ranking? The way is pretty interesting. So basic says that, let me just, so let's focus on this graph first. I think this would be pretty illustrated. So we have 3 distributions for candidate 1, candidate 2, and candidate 3. And we can generate a ranking. Now let's try to give every candidate something called a latent utility. So just think about it. Here is an item, here is a presenter. You don't know your preferences over it. You want to estimate its quality. But your estimation is somewhat noisy. You don't directly observe its quality. You must use it. But I mean, the way of using it is more like sample a utility from its true utility distribution. If this is a very nice quality presenter, you probably will have a very nice, with high probability, you'll have a nicer experience. But if it's a very poor one, probably with high probability, you'll have a poor experience. By the way, this is really a poor one. This is a ripoff. seriously. So I was buying it at Walmart and then asked for a return. It looks almost exactly the same as this one, but anyway, so they returned the money because I said, if you don't do it, you will be sued. I got really annoyed at that point. So actually, I should report anyway because this is this is what we should do, right? So report this report. Even in that state. In China, well, we all have our reports. Right? Anyway, so this is not recorded, right? I didn't say any bad thing about China. China is great country. All right, so now we have generated one utility value from each of the distributions. So that's kind of your utility. You can just have one sample. You can have multiple samples, but mathematically the same thing. You can have one, everyone is one sample. Let's say everyone have a perceived utility, in statistical terms, a latent utility, about this candidate. So you're going to fix U1, U2, and U3. And then you just rank this candidate with respect to the perceived utility. You don't directly report this perceived utility because maybe you don't realize. For example, I look at, I would say, oh, this is pretty nice. And then after I used the repop, I said, well, it's terrible, but I don't really want to quantify how much I like it, how much I don't like the repop one. I just want to compare it. It's pretty easy. So that's kind of modeling how people may generate preferences. Okay, so 2 steps. Given the parameters modeled by distributions, everyone first sample a utility, latent utility from each of the distribution, and then you rank this candidate with respect to the perceived utility, and that's going to be your ranking. So I'm just describing the third part of the statistical model, given the ground truth, generating a distribution over samples. Okay, very important class of statistical models. So mathematically, it basically just says that given the parameterization, theta 1, theta 2, theta 3, the probability of generating a ranking C2 preferred to C1 preferred to C3 is a probability that you independently sample this latent utility from each of the distributions, and that the probability that is compatible with the ranking just submitted, right? So U2 is strictly larger than U1, strictly larger than U3. So I'm sure that everyone is smart. You can immediately build in your mind what is mathematical formula, this very long integration of calculating this. But I'll come back to the calculation in a few slides. Okay, so just to be more clear, under random utility model, how would you generate a profile? Profile means a bunch of rankings, the set of rankings collected from the voters, or in other words, it's just the data. Sorry, so in social choice we call it profile, but sometimes we should just call it data. So every data point is going to be generated independently and identically. So that means given the ground truth parameters, which has 3 distributions, you're going to generate agent 1's ranking independently, then you move on to agent 2's, and you're going to generate all of n agents' preferences independently. So that's the generation process. Now, any question about the random utility model in general before we talking about 2 special cases? Might be some confusion over here. Yes?
Try modeling the agent preferences.
Sorry, what's that?
What are the agent preferences?
Agent preferences. So I think you're asking about a question that not really directly. So the 2 ways I would think that you're asking the question. So I'll try to answer you according to both of my understanding. So you're asking how am I model agents preferences? So the first understanding to this question is that the agents preferences are modeled by 4 rankings, and that's the data reflected. And the second understanding of the answer to your question is that you may ask, probably, like in recommended systems, we're going to model every agent's preferences, and then we're going to recommend items to them. So we are currently not doing that part yet. We are not kind of doing like a personalized modeling. So here's more like a bunch of data, and we want to kind of treat of them as, you can think of this way, a single person asking the same question, ranking the set of candidates over and over again. So you can think of this, we're kind of learning this set of agents, a whole group. We're learning that group's preferences. To some extent, we're doing that. But certainly, in like modern student questions, we have extensions of it to this kind of personalized set. Not sure if I answer your questions, but please stop.
Yeah, that's basically, yeah, I get.
Oh, okay, so please, so we can talk about so, all right, thanks so much for asking. Any other questions? If not, so let's move on to two special cases. Probably the most famous special case is called the Plackett-Lewis model, sometimes written as PL. It's a very strange way, I would say. The way I'm defining it is pretty strange, but it's a very beautiful characterization. It turns out like that. So, if you plug in something called a Gaussian distribution, which I didn't know 5 years ago, and I still don't remember exact definition, but it's more like almost a bell shape. It's kind of a bias, the shifting towards the left. So, but it's kind of smooth and a nice bell shape. If you plug in the Gaussian distribution, then what you get is a random utility model that have a different parameterization, a more natural parameterization discovered independently by, I'm sure it's been really discovered many times, but essentially it's just random utility model. But here is a different reparameterization. Say every candidate, every alternative is parameterized by a number, a quality number, strictly between, let me think. So it doesn't, yeah, strictly between 0 and 1, it doesn't really matter. Then it doesn't have to be strict. So between 0 and 1, let's say. So then the probability of generating a ranking is can be written down as the following very nice way, which is, so think about what's this. So given the ground truth qualities, the probability of generating a ranking, C1 prefers to C2, prefers to C3, all the way down to Cm, is the following formula. So what is the first term? The first term represents the probability that C1 is chosen among C1 through Cm. So sometimes, I mean, this part is more like a discrete choice model. You're given a set of candidates C1 through Cm. You are choosing C1 as the top choice. And by the way, sometimes I say candidate, sometimes I say alternative. These two terms are pretty much the same in this tutorial. Okay, so and then once you have done that, the second part is what is probability I chose C2 among C2 through Cm. So that's kind of natural because you can think about it in this way, right? So C1 is in the top means that C1 is ranked ahead of the rest guys, means that if I give you every alternative, you're going to choose C1. And the second part says that let's don't think about C1 anymore. Let's focus on C2 through Cm. If I'm going to give this candidate, you're going to choose C2, and the probability of doing it is proportional to the quality of C2, and so on. Okay, and this pretty much is just a very similar and generalized logistic regression. And the nice thing about it, the best thing is that it's computationally trackable because at least we have an analytic solution, this formula, to the likelihood function. So likelihood function is just the probability of the data given some ground truth. So that's pretty nice because then you can use whatever techniques to compute the maximum likelihood estimator, which I'll be slightly more clear in a few slides. And it's actually the only random utility model among this class that is known to be computationally tractable in the sense that it has a nice formula. Because once you have this formula, you can just throw it to MATLAB, for example, or whatever your best or your best solvers to compute the maximum likelihood estimator, which is actually what we did in the first place, but we'll see. It's very widely in economics. I'm just listing a few just because some of them are relevant, but just please keep in mind that all of the applications I listed in the first or second slide, remember that many applications, actually people have studied how to use Plackett-Lewis model in all of them. And of course, I mean, in general, random tuning model. So it's a very widely applied model. McFarland Nobel Prize, certainly not for this model, but for discrete choice model in general and some kinds of mixtures, but it's closely related and the idea are pretty much similar. So the bad thing, I won't say bad thing, but somebody said yesterday, right? So one of my friends, but I don't remember whom. If you cannot do the best thing, you are do tractable thing. Maybe one of my friends is whoever said that was sitting in the audience, but I just don't remember. So sometimes it's not the best model, as we're going to see later. I'm going to show you hard evidence that sometimes it's not as good as other models. So this is Plackett-Lewis model. Any questions? All right. So another, okay, so I forgot this slide. So very quick visualization of Plackett-Lewis model. The way of thinking about generating ranking can be visualized as you are taking bars out of an non-transparent urn. Let's pretend that we can look through this urn. Say we have 4 bars represent the 4 candidates. And the radius of bar are the parameters. Say the red bar has the parameter 0.4, 0.3, green 0.2, blue 0.3, and yellow 0.1. They happen to sum up to 1, but it actually doesn't really matter. So now the probability of generating a ranking corresponds to the probability of your taking this ball out one after another from the urn. And the probability you're taking a ball is proportional to its size. Well, to its radius, I have to say. Size is radius cubic. It's geometry. But anyway, let's pretend this is a 2-dimensional ball. Let's do it. It doesn't matter. So the point is that, okay, so here is the example, right? So given 0.4, 0.3, 0.2, 2.0, what is probability that the generated ranking is red, blue, green, yellow? It's certainly not 1, not 1. So it's actually the probability of taking out red ball first, which is 0.4 over the rest of the weight of the rest of the board, which is 1. And then the next one, we're going to take out blue ball, which is 0.3 over 0.3 plus 0.2 plus 0.1. And we're going to take out the green ball, which is 0.2 over 0.3. Okay. Now, this is a Cottagers model, very nice parameterization. It doesn't look like random utility model in the first place, but I think it was yellowed. One of the guys, they proved that it's actually common, and very nice theorems. Anyway, so Thurstone, in the first place, proposed to use Gaussian distributions as the utility distribution. That's actually a very nice choice, natural choice, right? So if you're going to name one distribution, I'm pretty sure that everyone says Gaussian, so regardless of situation. So it's a very nice idea, but the problem is that firstly, it's intuitive, it's more flexible than Gumbel distribution, because Gumbel, at least in the Cottagers sense, it's a fixed shape, but at least we have a mean and a variance, and it's more flexible. And the bad thing is that this used to be believed to be computationally intractable, just because there's no analytical solution for the likelihood function. Of course, there are many sampling-based approaches or whatever other optimization-based approaches. For example, this is natural generalization of a probit. We all know that probit is tractable, of course. But in general, when you have more ranking, if you're not dealing just the one probability representation problem. Okay, so why this is hard? Well, that's the time we can take a closer look at the scary formula. Say, given the ground truth parameter, which should be small data, what is probability of generating C1 versus G2 all the way down Cn? Well, it's actually just the probability of generating the latent utility vectors satisfying this constraint. So this integration, the last one, the first one actually is about the last candidate. So the last candidate's utility can be from negative infinity to positive infinity. But then the point is that the second to the largest candidate's utility, um-1, must be from um to infinity. So because we know that it's compatible with cn-1, strictly larger, sorry, um-1 must be strictly larger than and so on. So that's why it seems pretty hard. So for the list, there's no analytical solution known yet. There's been some studies on approximations, but still itself is a pretty hard problem. Okay, so that's the random utility model, Gaussian, let's call it a Gaussian random utility model. Now, let me talk about a flexible way of combining this multiple existing models. This is called mixture models. You probably have heard of Gaussian mixture models. That's a similar idea, but here is a general mixture. Say we have k statistical models, M1 through Mk. They may have different parameter space. For example, theta1 might be different from theta k, but they must have the same sample space. Means that your observation must be the same under all of these k models. Of course, the probability distributions must also be different. The mixture model, we're going to define it. But we're going to define it in the statistical way, which is specifying the 3 parts. Parameter space, we have 2 parts in the parameter space. The first part is the Cartesian product of the individual parameter space of these k models. And the second part is something called a mixing coefficients, which is basically k numbers, kind of saying that what is probability that a random data belongs to one of these samples. And the sample space is the same as S, because every model has the same sample space. Now, the way of generating a sample can be visualized in the following way, which is we're going to define probability distributions of a data right now. Now, given this candidate, given this parameter space, we're going to first pick one of the models to generate our data. So we're not generating the data from any particular model, but let's say we're going to generate this ranking from either first model or second model or the case model, but with probability specified in the mixing coefficients. For example, we're going to use the first model to generate the data with probability alpha 1. We're going to use the second model with probability alpha 2, and so on. Okay? And then after you have chosen the model to generate your data, you're just going to use the specified conditional distribution in that model. Let's say probability I, if you happen to choose the one from our model. Okay, that's how we define a mixture model. Any questions? Very quick example: Plack-Lewis mixture models. Okay, so we have two Plack-Lewis models. Each have different parameters. So this is just like quickly telling you how can we generate data, right? So this is a ground truth parameter of a Plack-Lewis mixture model. So in the first model, we have 0.5, 0.2, 0.2, 0.1. In the second model, we have 0.1, 0.4, 0.2, 0.3. And mixing coefficients is 0.2 for the first model, 0.8 for the second model. Now, when you generate a ranking, you can flip bias coin so that 20% of the time, you're going to generate a ranking from the first Plack-Lewis model. And 80% of the time, you're going to generate the ranking from second Plack-Lewis model. That's how you're going to generate ranking in a mixture model. Okay? You can see that mixture model has more parameters, so it means that it's more flexible. It usually provides better fitness, but we haven't talked about model fitting yet. We're talking about it almost immediately, and it can be used for clustering because you would have some idea of like which. So if I'm a ranking, if I give a ranking, like I prefer red to yellow to green to blue, maybe you can say that I belong to the first model, but not the second model, and so on. Okay. Now, here is then just a quick example of how mixture model has been used and clustering has been used in the literature. So Goldman and Murphy used this to fit an election data set, Irish election data set. It's a real election data set, but only on the polling, so it's not real voting, real votes, because real votes are confidential. So the way to visualize it is that there are 5 candidates. Panoti means blue candidates, McAleese means the green candidates, Nally is yellow, and so on. So they used an K equals to 4 Plack-Lewis mixtures, 4 Plack-Lewis models to fit the data set. So the mixing coefficients are the width of each of these blocks. So for example, component 1 is probably 0.2. Component 2 is 0.25, 0.23 is 0.35, and so on. And within each column, the height of the block represents the parameter, those lambdas. Okay? So the larger the height, the more there's more probability people in this block would rank these guys in a higher place. So, I mean, you can probably draw interesting conclusions based on data using mixture models. And maybe they can say, oh, well, this 4 blocks corresponded to 4 voting districts, and this corresponds to whatever districts, and so on. Maybe you can draw some interesting conclusion of it. But decision making is much more complicated than just looking at parameter MLE and say something about that. We'll see an example later on in the second part. But this is just going to showing you how can we use mixture model. Actually, how have people already used the mixture model and interesting things. Okay, so we have learned 3 models so far, 3 types of the model so far. We have learned distance-based model, we have learned random utility model, and we have learned the parameters, so the mixture models. Okay, so now we have already seen so many models, but a common question that has been asked, especially when you are submitting a paper, not to ICML or NIPS, is that what if the model is wrong? So you're deriving everything just based on the model is ground truth, but what if your model is just completely wrong? You are just saying nonsense. This is a very valid criticism, as famous statistician, John Fox. I'm not working statistics, so I don't know how famous he is, but apparently if you Google this quote, it's extremely famous quote. Probably because it's just that he is the first to say it. All models are wrong. What's the point of doing this? So the point is that the second part of the quote is that some are useful. So it basically says that this is the limitation of statistics, right? So statistics assume something about the model, and then all of the theory is based on the assumption that the model is correct. There's nothing you can do. What if your model is wrong? What if think about it in a wider scale, right? So what if your physics, this Newton's first, second, third laws are wrong? Well, I mean, that's the same story. So, but what we can say is that the point is that using this type of models, what decision can we make and are they useful? And of course, it turns out sometimes it's useful when you say, oh, this is going to drop out. Or it's not useful. Newton mechanics is not useful when you're looking at this scale, right? So it's hard to say, but it becomes more like an empirical question rather than a theoretical question. So what I can say now is that we have 3 types of models, and they're widely applied. They have been proved to be useful in some cases, and probably they'll also be useful later on. But if not, let's build a new model. Let's find new tools. For example, machine learning, automatic model selection, right? So that's the thing that you cannot get rid of. So just don't be too hard on this point. That's my take point. So you certainly can, but we still need to make a decision. We still need to give somebody an offer. We cannot say it's not Mal's model, so I'm not going to hire you guys. That's a terrible argument. Okay, so now the question is that which model is more useful? Well, how can you say a model is useful? And for what purpose, actually, more importantly? I mean, it certainly can be useful, but is it useful for entertainment? Is it useful for training graduate students? But we're going to see that this is actually a problem that will be more talked about in the decision-making part, because there, we are still missing an important component, which is what is the quality of the decision. We really haven't talked about decision yet. We're just talking about how can we model the ground truths, how can we model your statistical knowledge about the data. Okay, so, but right now we're going to talk about model selection. Of course, statisticians have thought about it. You have multiple models at hand, you have some data, which model best fits the data, and which model should we use for the future. To some extent, this is what machine learning is doing, right? So you have training data, test data, held out data. You are training some models and use held out data to choose the best model. So to some extent, everyone is doing model selection, some automatically, some not automatically. But let me just, I'm sure that many of you are familiar with machine learning, but some of the model selection criterion are, we're going to discuss this. Okay, so now what is a good model? Of course, we want to be as predictable as possible, but all of us know the notion of overfitting. Means that if you have too many parameters in the models, it's, of course, it will likely have a better prediction. That's for sure, because it's logically true. Now, how can you kind of use a nice single measure to say we have t parameters, we have n data points, and we do some model, we do some estimation thing, and how can we measure the fitness of the model? So you can do it by log likelihood, more like to some extent it's a smooth version of the arrow. So now theta star is the best parameter you learn from, let's say, the training data. Let's say, I mean, here you can say D is training data, D is testing data. You're doing strange things. So, but if you have just a few small data set, that's probably the only thing you can do. Okay, so just look at how well your best trained parameter fits the model by looking at the log likelihood. Likelihood tells you how well the best parameter would approximate the data. Or you can do the standard machine learning thing. You have tested data, you learn theta star from the training data, and then you look at predicted log likelihood. So I don't know why I'm taking E. Maybe this is a typo over here. Maybe it's just that you have multiple test data that you're going to take the expectation, but it doesn't really matter. So we should be freely. I remember this. But the two somewhat strange ones are called. First one is called IJCAI information criterion, and you can see that it's named after somebody called IJCAI for sure. There's some interesting theory behind it. So which I I'm not actually, I used to learn it a couple of years ago, but I don't want to say too much. So if you really care about why this is good information criterion, you should Google it. And there's really interesting theory behind it. But basically it says that you're going to consider both the number of parameters as well as the likelihood, especially log likelihood. So the second part is log likelihood. The first part basically says that, so, oh, by the way, AIC, the smaller the better, as you can see. So if you can just use one parameter and you achieve the same likelihood of whatever data, test data or training data, it's better than you are using a two-parameter model and achieving the same likelihood. Okay, so very high level, that's kind of the quantitative comparison we can draw. So, and another thing is called a Bayesian information criterion, which has a similar idea. The only reason I'm moving it looks like I'm emphasizing BIC, but actually not, just because it's too large to be on one. So I don't know which one is better, but people use both. People actually probably use many others, but these are two the most popular two. So it's a slightly different form. The second part is still -2 log likelihood. The first part is t multiplied by log n, but not 2 directly. So log n, remember, n is the number of data points. So for whatever reason, BIC use this. So if some of you can explain, I'm very happy. But I don't want to say something wrong, especially it's like here. But it's something related to like you have a 4-parameter space, many parameters. Now, what if you use a subset of parameter? You use a larger set of parameter, and then there are some asymptotic theory saying probably this is the best kind of measure, saying which one can have. I think you mentioned in terms of generalization error. So, but anyway, so it's kind of the direction before video recorders have. Anyway, so we actually have done some experiments testing, like which I said previously, Cottagers model may not be the best fit, but how can we say that, right? So you can imagine that it's not the best fit, but in practice, does this happen? We did some experiments comparing the mixture models of Cottagers, mixture models of random utility models. We're going to show you some results. Prefleaf org, which is, I think it's by far the most famous or largest data set by Cottagers Group and New South Wales, produced in Australia, by the way. So it's great to say it here. Also by Tech, which just moved to IBM Research, very close to my university. So there are many data sets over there. Some are partial orders, some are weak orders. And we found 209 data sets on full rankings. The number of candidates ranges between 3 and mostly 12. And here are the results. Remember, we have AIC and BIC. I'm going to show you very quickly. So numbers are boring. Don't read the numbers. If you trust me, I can just tell you the conclusion. So what does this number mean? We're not showing the AIC, BIC, but we're just showing which AIC, which AIC is better than another. So this is more like a term tournament graph. Say Cottagers versus Cottagers, which one is better? Of course, 0% is better because it's exactly the same thing. So let's look at this. Probably a more interesting number is this: Cottagers versus RUM, random utility model with Gaussian distributions. So previously I claimed that Cottagers model is not always the best. Now let's compare the AIC. For 23% of time, AIC of Cottagers is better than the AIC of random utility model with Gaussian distribution. So we are running on 209 data set. And this comparison is statistically significant. I'm not showing everything. So you can see that this is kind of symmetric. RUM versus Cottagers for 76.6% of the time, RUM is better than Cottagers. It's better than Cottagers data set according to AIC. And now let's look at Cottagers and K-Cottagers, which is the mixture of Cottagers models. Because you would say, well, using mixtures, we have more parameters, so it's not clear which one is better, which is totally true. But let's look at just the PL versus KPL. So certainly Cottagers, well, Cottagers is not better than a mixture of Cottagers, but mixture of Cottagers is 90.4 times percent of times better than Cottagers. So you could say, what are the remaining about 10%? The remaining 10%, they are exactly the same because Cottagers is a subset of K-Cottagers. So on some data sets, the best fitting one among this mixture is just using one single Pleclius. So we can use one Pleclius, two Pleclius, three Pleclius, and so on. Choose the best K Pleclius, and sometimes it's one Pleclius, and that happens with about 10% of the time. So, but basically, if you just quickly look at it, so KRUM, mixtures of random utility models with Gaussian distributions, is pretty much just dominating everything else. So that's our conclusion for AIC. And for BIC, very similar. So K-RUM is dominating Pleclius, dominating K-Pleclius. It doesn't seem to be dominating RUM itself, but notice that it doesn't just at 40% of the time. It's better than a single RUM, and it's different. So for the rest of the time, about 60% of the time, a single RUM works best among the class of KRUMs. Okay. Showing you some evidence about model fitting. Now, what are the observations? Again, these numbers are boring. Observations are basically from the pref-lib for ranking data, which we think is pretty representative and pretty nice data set. We can at least rank this models with respect to model fitting result using either AIC or BIC, same ranking. The best one is random utility model, Gaussian mixture model. The second is a mixture of Pleclius model. The third is random utility model with Gaussian and Pleclius model, unfortunately ranked at the last. So you can see this is somewhat natural because we know that Pleclius is most computationally trackable. It has an analytical solution to the likelihood functions. You can just use whatever optimizing technique. Random utility model is slightly hard to tackle logistic regression, but it's still not impossible. Mixture model, we're going to talk about mixture model later on, but I'm not going to talk about the algorithm, but this is kind of the most recent research. People have been working on it, and the random utility model, mixture model, we have some papers kind of in submission to some extent. I don't want to repeat too much detail, but so it's pretty hard model, I have to say. But if it is best fitness to some extent, then it's probably worth time putting into trying to make these models, training models as much as possible. Okay, so the conclusion is that some models are more useful, and the next part is that how can we make use of them? How can we learn maximum likelihood estimator or Bayesian approach based on each of these models? Not really each of them, but I'll pick the most exciting and the most interesting ones, and hopefully you also have fun. So we have 10 minutes before the break, so let me just move to the next part and see how far we can go. I know coffee break is really a thing we should never miss, so remember that I set our alarm clock. Coffee break, where is the second part? Okay, so we have finished the introduction. Now let's talk about the inference algorithms for these models about rank data. And remember that we want to tackle the problem from the perspective of statistics, economics, and computation. And for now, especially for the second part inference algorithm, let's completely forget about economics, completely forget about strategy proofness, about fairness, which will come back on the third part. So on the second part, we're going to still the first part. On the second part of the first part learning, we're focused on the intersection of statistics and computation. Mostly we'll be talking about maximum likelihood estimator and the Bayesian approach. So what is the maximum likelihood estimator? I'm sure that many of you are familiar with, but let's just very quickly go through the definition. So remember, this is a generative model, right? So we have, given the ground truth parameter, you have distribution, IID distribution over the data points. Again, IID is not necessary, but we're going to assume IID distribution in this talk. So we've given any preference profile, we call it preference profile, but it's just the input data points. Each of these data points has the linear order for ranking over a set of alternatives. The likelihood of theta with respect to this data set is denoted by L theta P, which is basically just the probability of generating this data under the ground truth distribution for theta. And because of IID assumption, it's going to be just take each of these votes from this profile. Let's look at the lookup table of the distribution given theta, and then let's just take multiplication of all of these things. Now, this gives us a famous MLE, maximum likelihood estimator mechanism, which basically just says that we're going to choose a parameter based on the data. Okay, so let's say the data is P. Let's choose the parameter that maximizes this likelihood. That's it. Very simple definition. Now, in general, maximum likelihood estimator is pretty much the one to use. For example, you want to estimate what is the average temperature of Melbourne, for example, and you have some ground truths, and then you have some samples, and then you calculate sample mean, for example, calculate the MLE under some statistical model. But there's one particular point I want to raise is that MLE gives you an estimate in the parameter space, right? Because it tells you that, so if I have the data, sorry, this should be P. If I have the data, I'm going to tell you a parameter. This itself doesn't mean much. If your decision is which parameter is most likely, probably this is a good approach. But if your decision is something different, as we'll see later on, this may not be exactly the approach to take, which I hope I will be more clear rather than confusing at this point. So let me quickly fix this so that we all right. Now, the Bayesian approach, it's basically it's just a different school of thoughts. So, given the preference profile and a prior distribution pi over theta, prior distribution just describes like how likely do you think each state of the world happens without looking at the data. For example, I would say, well, the average temperature of Melbourne might not be very high because this is a city by the sea, or because of my friends told me it's a very nice weather here there. So maybe I would say the average temperature is 18.5 rather than 90, for example. So maybe before looking at data, you have some kind of prior belief information about it. Now, suppose you have the data. Now, how would you do inference? Let's say first we're going to calculate the posterior probability, so the posterior probability of the data parameter space using the Bayes rule, which is almost the same as just likelihood inference, except that the probability of any particular theta given the data is proportional to not just the probability of P under theta, but also weighted by how likely every the prior probability is. So for example, if I'm still trying to look at calculate the average temperature, and I suddenly see that there's extremely cold days like today, it's, I don't know what's temperature today, 7. And am I just immediately believe that the average temperature is, for example, 7? No, because I have a strong belief that average temperature is 18 or something. So maybe this type of evidence shift me a little bit towards 7, but still you need to consider your prior belief. But then the problem is how to set the prior belief. There's the whole literature in it, and I don't want to talk too much about it. Okay, now suppose you have the posterior belief, posterior distribution over parameter space. How can you make a decision based on posterior distribution? I'm just going to talk about one of the most straightforward ways, but again, I would defer it mostly to the decision-making part, where you need to consider the consequence of the decision. But here, let's just talk about a similar thing to a maximum likelihood estimator. This is, I never got this pronunciation correct, maximum posteriori MAP estimation. So it's better to just remember its math. When I was looking for, every time I give talk, I have to look for the pronunciation online. And yesterday, I looked at the online, and somebody commented in the video that, why do the statistician teachers always use this French? And we all know that this is not French. This is Latin, right? Am I right? This is Latin. So I mean, it's really a little bit annoying, right? So when you say MAT, I was calling it MAT all the time, and then until some student asked me, what is MAT? And I answered some strange, random things. And then I know I think it's wrong, so. But anyway, MAP is basically just choosing the parameter that maximizes the posterior distribution probability. That's the same, technically the same as MLE. This is a very confusing part. Technically, MAP under uniform prior is the same as MLE, but it doesn't mean that MAP is the same as MLE. It's just a different thought, school of thought. But technically, at some point, they're same mapping. So So very quick example. Still for our favorite Cottagers Theorem setting, we have two candidates. One is correct, one is wrong. And let's now set the P, probability of voting for a correct candidate, to be 0.6. And let's say now we have data collected of 10 voted for Obama, 8 voted for McCain. Let's see, according to the MLE, how can you compute MLE and NAP? Okay, so MLE is that the likelihood of Obama is like this. So just plug in the formulas. Wait, why I'm having? I'm sorry. There should be 10. So why I'm having? Yes, great. So sorry, typos. So let's just look at this. So it's suppose the ground truth is Obama. The probability of this for this 10 votes voted for Obama is 0.6 raised to the 10 multiplied by 0.4 raised to the 8, and similarly probability of the McCain to be the ground truth. The likelihood of McCain to be the ground truth is 0.4 to the 10, 0.6 to the 8, and it's easy to see that likelihood of Obama is larger than likelihood of McCain. So if you're going to use maximum likelihood estimator, Obama would be winner. However, if you're going to use a strange prior, which is very biased towards McCain, you firmly believe that you're a Republican, you firmly believe that McCain is the best candidate in the world, even though there's a small chance that Obama might be not as bad. So then you would do the similar reasoning, except you're going to weight the posterior probability to some the likelihood, and then you compute the posterior, technically compute the posterior probability, and eventually you will reach a different conclusion. So just an example of how can we do it. So this slide is mostly meant to be, if you want to look at the slides of this tutorial, so just do a very quick exercise by yourself. So I'm not going over all of them. Okay. So great. So it's 9:59. So I think it's coffee time. So let's come back at 10:30. And if you have not voted, please vote. And we'll see some interesting conclusions at that point, hopefully.